Hi, my name is Jakub Beránek, and I would like to show you some design trade-offs of CPUs and memories that can affect the performance of your programs. I'm a PhD student in Ostrava in Czech Republic, and I also work as a research assistant in IT for Innovations in Ostrava, which is a supercomputing and HPC center. And my interests include HPC, distributed systems, and program optimizations. And because I work in HPC, I naturally care a lot about the performance of my programs. And to extract the most performance out of my code, I need to follow some steps. So first, I need to select the right algorithm with the best complexity. I need to implement it using a low overhead language with some minimal runtime. I prefer Rust, but I heard that some people still use C and C++. You have to compile your program properly. You have to use the best optimization passes available by your compiler. But you also have to tune your code to the underlying hardware. And I think that this is something which is very important, and it will become more and more important in the upcoming years. Because if you know something about the specific CPU or memory hardware that you will run your program on, you can exploit this knowledge to extract more performance of your code. Some people might say that this is not important today, that this is stuff of the past, and the compiler will deal with everything. But I'd like to show you today that this is not always the case. And I think that we should care about this because there is a fundamental abstraction gap between what we write and what we execute. When you write C++ programs, you write code against the rules of the C++ abstract machine, as is defined in the C++ standard. And this is a relatively simple and sequential executing machine. And the Intel CPUs, they try to fulfill the contract of this machine. They try to provide the same outputs for the same inputs so that they behave like they are following the C++ rules or whatever other language. But in reality, the Intel CPUs are incredibly complicated, and they are doing a lot of funny stuff and heuristics inside just to be faster. And if we try to understand more what are those trade-offs inside the CPU, this can get us more performance. Here's a simple example. This is a simple loop that just goes over all elements of an array and increments them. And if I was interested in the question, how fast are the individual array increments? Are they all the same speed, or will some of them be slower or faster? If I'm only following the C++ standard or the rules of the machine, all the increments have to be the same size, right? Like there is nothing in the C++ standard that will say some of the increments might be slower or faster. At least I think so. I haven't actually read the standard, but it doesn't make sense for there to be something like this. But if I know that I will execute this piece of code on an actual hardware, for example, an Intel CPU, I know that those CPUs have caches. And I can predict that, for example, the first increment might be a little bit slower, because if the first element is not in the cache, it will have to be loaded from memory, and this will take some time. And the additional increments will be faster, because the elements will hopefully be prefetched into the cache by the time that we do them. So knowing about the hardware that executes your code allows you to exploit this knowledge to get more performance, and we will take a look at some situations where this happens. I would like to talk today about things that I call hardware effects, because I don't know about the better name. And I define this as performance effects caused by a specific CPU or memory implementations, which demonstrate some trade-off, heuristic, or just some design decision that some guy in Intel made 10 years ago, which is now affecting your programs. And as I showed you, it is impossible to predict such effects just by looking at C++ code alone. If you don't know anything about hardware and you just write C++, you can hit weird performance situations because you simply don't know what is going on in the background. So where is this complexity or those trade-offs, where are they coming from? This is a chart which shows the progress of CPU design or performance in the last 40 years. We see that the CPU frequency in the middle has been steadily increasing, which was great because our programs became faster without us actually doing anything. But at the year 2005, it kind of hit a limit, and the frequency cannot increase anymore because our CPUs would pretty much explode. But we can still see that even before 2005, the number of transistors has been steadily increasing. So where are those transistors going? One obvious answer is that they are adding more cores, right? So this is obvious from the black dots. Yes, we are actually getting more cores in our CPUs, but this is not all, because we see that even the single thread performance of our CPUs is increasing, even though the frequency stays the same. So how is this possible? It is caused by changing the microarchitecture of the CPU. This is the beating heart of the CPU. Specifically, this is the microarchitecture of Haswell, taken from the Intel reference manual. This architecture is already several years old, but it is still relevant because the newer architectures are building on top of it. It's divided into two parts. The front end, which takes care of loading instructions from memory, decoding them from the complex x86 instructions into simpler micro-ops, and putting them into some kind of buffer where they wait to be scheduled. They are then scheduled on some number of execution ports, which can execute, for example, integer arithmetics, floating point arithmetics, or load and stores to memories. And once they are executed and reordered in some way, because Intel CPUs, or at least x86 Intel CPUs, are out of order, they will be eventually put inside memory through the cache hierarchy up until DRAM, or just written to a register. And by understanding all of those little boxes inside this microarchitecture, we can learn something about how our programs will be executed and how can we make them faster. So how complex exactly is this microarchitecture? You are C++ programmers, I assume, so you know about the C++ standard, and the final draft of the C++ 17 standard has more than 1,600 pages. So it is a pretty complex document. However, this didn't stop the Intel guys, because the Intel x86 manual, which is like the holy Bible for Intel CPUs, has almost 6,000 pages. So the complexity of the hardware, I would argue nowadays, is even more complex than the complexity of our software. And if you want to really extract the last drop of performance from our code, we should start looking under the hood of our CPUs more often than inside the C++ standard, for example. So what I want to show you in this talk, some example C++ programs that are short and hopefully comprehensible, and all of them will be compiled with O3. I think that this is very important, because if I just showed you some weird performance behavior in debug mode, you could say, oh, the compiler will solve this. But it can do it sometimes, but not always, so everything will be compiled with full optimizations. And I will try to demonstrate some weird performance behavior, hopefully, with those examples. I will let you guess what might cause it. I will explain a possible cause that I think, like, what is happening. And I will show you how to measure and fix this. First disclaimer, everything will be Intel x86 specific, because this is what I have in this laptop. And also, I'm not an expert on this, this is just a hobby. So if you spot some kind of mistake, if you think that I'm measuring random noise, let me know, hopefully at the end of the talk, so it at least seems like I know what I'm doing. Now, this will be a live demo, so wish me luck. Now let's see some examples and start with something pretty simple. I will be using Google Benchmark for most of my experiments. If you don't know it, it's a library from Google that allows you to simply define a benchmark and then run it a lot of times repeatedly. So mainly I'm interested in this function called filter loop. And this outer loop is simply just a way how to tell the benchmark library that you want to execute something multiple times. So we don't have to really care about that. They're just iterating the benchmark so that you reduce noise. What I want to show you and benchmark is this. It's a loop that goes over a vector of floats, and it has a simple if condition. If the element from the vector is smaller than 6, I will add it to some sum, to this variable called sum, and that's it. So I will repeatedly execute this loop. Now, how does the vector with the data look like? I just generate a uniform integer distribution from 1 to 10, and fill a vector, I'm writing about 30,000 numbers. So it is just a medium-sized vector of random numbers from 1 to 10. So about half of them should be smaller than 6, and another half greater or equal to 6. And specifically, I want to benchmark 2 variants. In the first variant, I will simply generate the data and run my benchmarking loop. In the second variant, I will do exactly the same thing, but right before I run the loop, I will sort the data so that they will be sorted from the smallest to the largest. So this is the row that sorts them. And I'm not benchmarking the sort. The benchmarking is only happening inside this filter loop. So let's take a look what happens. Let me compile, okay. Okay, so now we run those 2 variants. The first one is when it wasn't sorted. The second one is when the array was sorted beforehand. And we can see that the variant where the data was sorted was more than 2 times faster than when I didn't sort. And I can run it again, but you can see that it already executed more than 5,000 times. But okay, if you don't believe me, we can run it again. And the result is pretty much the same. So somehow when I sort my data, suddenly my loop, which filters elements more than 6, gets more than 2 times faster. So this is a pretty classical example. Any guesses what might cause this? Yes, it has something to do with branch prediction. And again, if you just look at the C++ code, there is absolutely nothing that would give you a hint that something like this might happen. If you don't know the hardware that you're executing on, nothing will help you. You just have to look at the Intel manual, because nothing in the C++ standard will tell you that something like this might happen. And so actually when I saw this for the first time, I was pretty surprised. And it turns out that I was not the only one, because this is actually code inspired by the most upvoted Stack Overflow question of all time. And it asks, why is it faster to process a sorted array than an unsorted array? This is already a year old, and it had more than 22,000 upvotes. Right? So people are actually surprised that this is happening, because a lot of people don't know how the hardware actually works. And if you have no clue what is happening, if you didn't see this Stack Overflow question when you were randomly clicking links on Stack Overflow, you can use some kind of a profiler. If you are a student or if you have a lot of money, you can use this very nice tool from Intel, which is called Intel Amplifier, or also VTune. And if you run microarchitecture exploration, so we are interested in microarchitecture and we want to explore it, it will show you this nice table which tells you which little box inside the microarchitecture might be causing problems in your program. And it will also give you this pretty nice graph, so it shows you half of my performance is kind of going down the drain because of something called bad speculation. Okay, I might not know what that is. And it also tells me that it is front-end bound, so probably I should look at the front-end part of the microarchitecture, which was shown in red before. If you don't have money to afford VTune, you can also use perf, which is a very powerful profiling tool, which is free, and it is built directly inside the Linux kernel. And if you run perfstat on your executable, it will give you some kind of overview what is going on with the performance of your program. And even if you don't know what those words mean, you can see that there is something weird. It says almost a quarter of my branches were missed. So there were more than 100 million misses. And even if I don't know what that means, I mean, that sounds kind of scary, right? Like, my branch were missed. Like, where did they go? What is happening? So to understand what is going on, we have to look at this little box in the microarchitecture, which is called the branch predictor unit, or short, branch predictor. And to understand why is it even there, we need to look at the CPU pipeline. So this is a very simple diagram showing a pipeline of some simple CPU. Modern CPUs divide the execution of instructions into multiple steps so that they can process multiple instructions at once. Here we have 4 steps: fetch an instruction, decode it, execute, and write back to memory. And the columns are individual clock cycles. On the right, I have some assembly, but it's not understand if you don't understand it. It's not important if you don't understand it. We just need to look at this conditional jump. So at cycle 1, we fetch the first instruction. At clock cycle 2, we decode the first and fetch the second. At cycle 3, we decode the second, execute the first, and fetch the third, and so on and so forth. However, at clock cycle 5, we have a problem, because this green instruction is a conditional jump. So it decides at the runtime what will be the next instruction to execute. And it decides based on the result of this compare. And since at clock cycle 5, the compare is still executing, we don't know the answer. We do not know which instruction should we fetch. Should it be the instruction below 11, or should it be the instruction 15 if the conditional jump was taken? And because the CPU doesn't like to wait, doesn't like to waste time in this pipeline, it has this branch predictor unit that tries to predict. It just guesses. Based on the history and various heuristics, it tries to guess if this branch will be taken or not. And the important thing to know is that if it mispredicts, if the guess is wrong, this can cost up to 15 or 20 cycles on modern Intel CPUs. So it's pretty expensive to have a lot of branch misses in your code, especially in tight loops. So here is an example with the unsorted array, which has random numbers. Remember that we are checking if the number is smaller than 6. And let's say that we have a very simple predictor which is naive, and which just predicts that the next branch will have the same result as the previous branch. And at the beginning, it predicts not taken. So 6 is not smaller than 6, the branch will not be taken, so this prediction is correct, green. However, 2 is smaller than 6, so this prediction is wrong, and because this predictor will predict that the next branch will be the same as the last one, it will change this prediction. The next one is correct, however, the next one will be wrong, and it will switch. The next one is smaller, so it will be wrong again, and it will switch. And if the numbers are constantly switching, this predictor will basically miss each branch up to some point. So we have only 2 hits and 6 misses. And of course, the branch predictors in Intel and AMD CPUs are much more complicated than this. They use sophisticated algorithms, even simple neural networks. But the idea is that if our data is random, there is no way to predict what will be the next thing. Like, there is no way to predict random, by definition. But what happens when we sort the array? Now, let's say that we again have this simple predictor, which begins at not taken. At the first one, it is wrong. However, then it will switch to taken. And then it will be right for a long time, because the data is predictable, it's sorted, until it hits the first 6. Then there will be a misprediction because it switches. But from that point on, it will predict not taken, and up until the end of the array, it will have hits. It will have hits, because the array is sorted, and everything to the right from here will be larger or equal to 6. Right? So by making the data predictable, we have helped the branch predictor to avoid the mispredictions. So here we have 6 hits and 2 misses. And so if you want to measure this, if you want some concrete proof that this is actually what is happening, we can use perf, and we can use a performance counter called branch misses, which asks how many times was a branch mispredicted. So let's try it out. Perf stat -e lets us select the counter, so branch misses. And first, I will run the variant without sort. And it gives us 100 million branch misses. If I run the sorted variant, it gives us only 400,000 branch misses. So if we sorted the data, we reduce the number of branch misses by several orders of magnitude. And this is exactly what is making the code 2 or 3 times faster. Right. So how can we help the branch predictor? first step, having more predictable data, which is probably the most important. We can also use some automation. So for example, profile-guided optimization, when the compiler will instrument the binary and kind of see what branches are being taken or not, apart from other things. And then it can restructure the branches to make it better for the CPU to predict their results or to remove cold code outside of tight loops. We can also try to remove unpredictable branches, which is sometimes possible. I will show how in a while. And there are also some compiler hints. For example, this built-in expect in GCC, where we can say, I expect that this branch will not be taken. However, this should be used with a lot of caution, because this might not actually do what you think it does. This is more for removing cold code outside of hot loops. And the Intel CPUs probably will, even if the GCC put some kind of mark inside instructions that this is taken often or not, the CPUs tend to ignore them and just to use their branch predictor. So can my compiler actually help with this? I used floats before. Now let's use integers. And let's see what's going to happen. Compile. Bam. Now it executes much faster because they are integers, but we can also see that the difference is pretty much gone. And even in this case, the sorted variant is slower, but it's pretty much in the range of benchmarking noise, because this is nowhere near the 2 or 3 times difference as before. Right? So somehow, now it was faster in the second case. So this is just pretty much benchmarking noise. So somehow the compiler was able to remove those branch mispredictions when I used integers. Right? Let's confirm this. Branch mispredictions sorted 800,000. Branch mispredictions without sort 400,000. So actually now the sorted variant has more branch mispredictions, and that is because I sort. Sorting itself generates a lot of branch mispredictions, but in this case there are not a lot of mispredictions in the code. So how is this possible? Let's take a look at our trusted tool, the Compiler Explorer. When I used floats, this is our loop. Basically, this thing is here in the assembly. And we can see that there are 2 conditional jumps. You can recognize them because they begin with this J. So this jump is kind of skipping over the addition if the condition is not true. And this jump at the end is just for the loop. And we can see that we have 2 conditional jumps per each loop iteration. However, when I switch to integers, nope, I don't want to save. This is the loop again. GCC was smart enough to kind of remove this conditional jump and replace it with cmove, which is a conditional move instruction. This instruction, as you can see, removes the branch. It just computes both of the results or both of the possible situations that can happen and write it to memory only if the condition holds. So it can, for example, use some masking to write some dummy value if it doesn't hold. So with this cmove, our code got faster, and the compiler was able to help us. But if I used floats, it didn't do it, it couldn't do it, so we had to know about branch mispredictions. And cmoves are not always faster than conditional jumps, but in this case, they are. Right. Apart from conditional branches, there is also another situation that needs to be predicted by the CPU, and that is when the target itself of the branch is not known at compile time. So this happens, for example, when you have function pointers, when you return from a function, because you can call functions from different places, and also when you call virtual methods. So I have another short example to see what might happen. Here I have a simple class hierarchy ABC. A has a virtual method called handle, and B and C both inherit from A and have some implementation for this handle method. Right? So it's you don't have to care about this ID. That's just for sorting the instances. And again, I'm benchmarking a very simple loop. I go over a vector of instances of A, and I just call this virtual method. So I have a vector of instances, I go over all of them, and I call a virtual method. And again, I have two situations. I do not sort the instances, I just generate them randomly, random instances of either B or C, or I first sort them by the instance type. So in the sorted variant, all the B's will be before all the C's. So they will be sorted by instance type. So let's take a look what happens. Again, we can see that the sorted variant is much faster, because if the instances are sorted, the branch target predictor can learn quickly that now it uses the implementation of B, and then it will switch to the implementation of C, which is not really possible when they are random. And again, we can confirm this. Misses, example 0B, benchmark, filter, no sort. Without sorting, 86 million misses. With sorting, 400,000 misses. Right? So this is exactly the same situation. So virtual methods is another situation when you might want to care about branch misses. Right. Now let's go to see another example. So this was branch mispredictions and the branch predictor unit, an important part of the front end that you should know about. Now let's take a look at something maybe more interesting. I want to benchmark, again, this loop at the top. I have a vector of pointers to an integer. So just a vector of integer pointers. I go through all of them, and I access the number behind the pointer, and I increment it. So this is the code that I'm benchmarking. However, there is a catch. I want to see what happens when those integers will have a different offset between them. So I want to benchmark those 5 variants. This number always says how many bytes are between each pair of integers. So with offset 4, there will be 4 bytes between the beginning of the first integer and the beginning of the second one. So they will be basically consecutive in memory, right? And the pointers will just point to the individual elements. With offset 64, there will be a 64-byte gap between each integer pair. Right? With offset 4000, there will be a 4000-byte gap between each integer. And I will be benchmarking this with vector sizes from 7 to 11. So huge vectors. Surely they will not even fit into my cache. Right? I have just 11 integers. Now let's see what happens. Right? So this is the situation where the integers are consecutive. It takes from 2 to 4 or 5 nanoseconds to process the array. When the offset grows, it seems like the time doesn't change much. However, when the offset is 4096, suddenly the time to process the array jumps from 3 nanoseconds to 30 nanoseconds. Even though I only am iterating over 11, 10, and 9 integers. Right. So what is going on? Any guesses? What? Cache line size? It has nothing to do with page sizes, but it's a good. Maybe it has. You can find another explanation, but I will show something different. But yes, it is kind of weird that this number is exactly the 4K, which is used as page size, usually in Linux. Yes, I heard associativity and cache line sizes. So it has something to do with cache. But it probably isn't something with the cache size, right? Like when you talk about the cache, you are usually interested in how big is my cache. Does my data set fit into the cache? But here I'm iterating over 10 integers. So surely 10 integers must fit into my L1 cache, right? Well, actually, sometimes they don't. So let's take a look at what happens. We will be talking about this blue box, the L1 cache, inside the CPU backend. And we need to take a look at how are L1 caches implemented. At least on paper, it's possible that Intel or AMD does something magical, but L1 has to be so fast that they probably cannot come up with something hugely different than this textbook implementation. So caches, or at least L1 caches, are implemented as so-called n-way set associative tables, and this scary name basically means that they are hash tables implemented in hardware. Because they are hash tables, they need to have some input key, and this is the address of a cache line. So on my 64-bit system, it will be 8 bytes, and the result, the entry that the cache holds, is a cache line. When the memory subsystem loads data from main memory, it doesn't transfer individual bytes to amortize the cost of the transfer. It uses chunks of bytes called cache lines. And usually on your commodity Intel CPUs, their size is 64 bytes. Okay, so this cache is basically a hardware hash table that maps addresses to cache lines. Let's take a look at an example. This is a simple cache which has size 8, so it can hold 8 cache lines. And when you have a L1 cache, you have to decide on a parameter which is called associativity. And this number is exactly this n in the n-way set associative cache. And this number tells us how many cache lines will there be in each bucket of the cache. Right? Since it's a hash table, it has some buckets. When you take an input, you hash it, you calculate into which bucket you should put your cache line, and then you search inside the bucket if you have some space. And so naturally, if the associativity tells us how many cache lines we have per bucket, the number of buckets will be the size of the cache divided by n, or the associativity. And this is a parameter. We can choose what will be this value. So we can, for example, say that each bucket will have exactly one cache line, which is called direct map cached. Or we can say there will be only one huge bucket, which will have associativity equal to the size of the cache. So we will have only one bucket, so we don't even have to hash the input, but we will have to scan through all the slots to find an empty slot. So this makes it slower. In the direct map case, you don't have to scan anything because you have exactly one cache line or one slot where to push each cache line, but you will have a lot of hash collisions. Because if you have more cache lines that are put into the same bucket, they will throw each other out. And you can use also some trade-off. For example, here I can use N2, so I will have 2 cache lines inside each bucket and 4 buckets total. And before we look at an example of this, let's also talk about how are the addresses actually hashed. So this is a 64-bit address, some pointer, and it's divided into 3 parts. The lowest bits are called offset, and they simply select a byte within a cache line, right? Because the cache line has 64 bits, so let's say in this case, the 6 lowest bits simply select which byte within the cache line you want to address. And since the cache works with cache lines and not individual bytes, this number is not important at all for the cache. It doesn't really care what is this number. What is most important are those following bits, which are called index bits. And those bits basically directly form the hash of the address. You take those bits, and you literally use them as an index to select the bucket. So that's it. You don't even have to do any kind of modulo, because you exactly take as many bits as you have buckets, or like logarithm of 2 of bucket count bits, so that you can exactly address your buckets. So when you have an address, you want to look into the cache, you take those index bits, and that selects the bucket. That's it. And the rest of the pointer is called tag, and this is used to match if 2 cache lines are actually the same cache lines. Because, for example, you can have cache lines that have the same index bits, and let's say even same offset bits, and therefore they will go inside the same bucket. But it may happen that they have different tag bits, so they are actually 2 different cache lines, so they will evict each other out. If they have the same tag, then you have a cache hit. Then you found the same cache line inside the cache. So a quick example, I have 3 cache lines, A, B, C, and their index bits are 0, 1, and 0. With the direct map cache, A will go into bucket 0, B will go into bucket 1, and C will go again into bucket 0, but there is already A, so I have to throw A out. So I cannot even hold those 3 caches inside this type of cache. When I use just a single bucket, I can put all of them inside because they will just find the nearest free spot from the left and I have enough space for them. When I use this trade-off with N2, I can put A into bucket 0, B into bucket 1, and C into bucket 0 again, but now I have 2 cache lines per bucket, so they fit. So everything is okay. And here you can already kind of see the problem that is happening with our cache. If our bucket gets too full, because the address is somehow mapped to the same bucket, they will evict each other out, and we can have a slowdown in our program. So let's take a look at the actual parameters of my CPU. This config or this command will give you the parameters of your cache. I have 32K size, 64 bytes cache line size, associativity N, and size 32K. Those are pretty standard parameters for modern L1 Intel CPUs. And therefore, by calculation, if I divide the size by the cache line size, I have 512 cache lines. And if I divide this by associativity, I have 64 buckets. Right? So my cache looked huge, like 32K, yes, but I have only 64 buckets. So now it seems kind of small. And I can only fit 8 cache lines inside each bucket. So again, a pretty small number. So what is going on with the different offsets? This is a simplified example when I have just 4 buckets and 2 cache lines per bucket because the actual configuration wouldn't fit, but I hope that you get the idea. So when you have offset 4, the first number, let's just say it's like zeros, goes into bucket 0. When you increment 4, you will just increment the offset. So it will be, the index bit stays the same, so it will go inside the same bucket, and the tag stays the same, so we will just put the numbers inside the same cache line. So all the numbers will go inside the same cache line. This is the most efficient way. No space is wasted, you just fill a single cache line. Everything is fast. What happens when the offset is 64? Again, A goes to the beginning. When you add 64 to this address, you will increment the index bit. And because you increment the index bits, suddenly B will go into a different bucket. When you increment it again, C will go into a different bucket. And again, D will go into a different bucket. So we will have a different bucket for each number. And remember, I have 64 buckets. I benchmarked 11 numbers, so no problem there. I waste 60 bytes in each cache line, but whatever, I have 11 numbers, so it doesn't really, I don't really care. And I distribute the numbers equally among the whole cache. Now, what happens in the interesting example when I have offset 4096? When I add 4096 to this number, I will add 1 to the tag. So I will have exactly the same index bits. So in this scenario, I will use the same bucket for all the numbers, right? So those 2 numbers already filled my bucket here. In the real scenario, it would have to be 8, because in this computer, it has associativity 8, so I have 8 spaces here. C will go inside the same bucket. There was no space, so A had to be thrown out. D goes inside the same bucket, so again, B had to be thrown out. So even if I have only 9 numbers, if I have associativity 8, I will replace the numbers in this one bucket repeatedly, and my performance will be 10 times slower, as you saw in the benchmark. Right, so same bucket, but different cache lines. When bucket gets full, we need to evict, it gets slower. So again, how can we measure this? There is a performance counter called L1D.replacement. So let's use it. It tells us how many times was a cache line loaded into L1. So basically, if we had a lot of evictions, we needed to load the cache lines into L1 repeatedly. So if this number is high, we had a lot of collisions. Replacement, example 1. Let's try the offset, unlock. Offset 4. So this is the best case where everything is in the same cache line. We had 100,000 replacements. When we try with offset 4096, we see that again the times are up to 10 times higher, and we get 500 million replacements, right? So again, we get several orders of magnitude more loads from the DRAM or the upper cache layers inside L1. And this is what makes this scenario slower. And this won't happen only with the specific number 4096. Each number that will only increment the tag and it will keep the index bits the same will have this problem. But if you remember the previous results, when I used a larger number, 4128, it was actually fine because it was incrementing the tag. But this 32, this number down here, was actually also incrementing the index bit slowly. So I was distributing the numbers along all the buckets. Right? So in this case, it didn't happen. So it's not caused by, it's not like I increase this number, it will get slower. It needs to be a specific value that will cause this problem to manifest. So if you have some weirdly aligned data that you are processing, it might happen that you will get a lot of cache collisions. So this is something that you should also think about when you write performance critical code. Right. There was a spoiler. Let's take a look at another example. This time I'm not using Google benchmark. I'm loading a floating point number from the input. I'm creating some vector of floating point numbers initialized to 1. And then I just go repeatedly over all the numbers and I multiply them by this loaded number. Right? So I load something from the input and then I repeatedly multiply it with some vector of numbers. That's all this program, I hope, is doing. So let's see how it reacts to different numbers. This time I have to time it. So let's try 0. It takes about 100 milliseconds. If I try 1, again, about 100 milliseconds. If I try 100, it's pretty much the same, about 100 milliseconds. Now what happens when I try 0.1? It seems that suddenly it's 3 times slower. Okay, let's try something different, 0.2. Also 3 times slower, 0.3. 4 times slower, interesting. 0.4, faster. 0.5, back to the original speed. Wow. So, what is happening? Is there some bug with my floating point in my Intel CPU? What might? Yeah, I also show it on the slide already, so if you paid attention, the surprise is gone. Yes, so this has something to do with so-called the normal floating point numbers. This is a representation of a floating point number in the single precision, so float. 30. Oh, I'm sorry. This is actually this is just 16 bits, right? I cannot even count. So this is half. This is the sign bit. Those are the exponent bits and the significant bits. And this is a kind of a special number because the exponent is 0, but the significant is non-zero. So if it was all zeros, it's just 0 or -0 if there was one here. But in this case, I have a 0 exponent and I have a non-zero significant. And this type of floating point number is called a denormal or subnormal floating point number. And it represents numbers that are very close to 0. And they are kind of different to process the normal floating point numbers. Their hidden bit is not 1 but 0, and they also have a different bias, so the exponent needs to be handled differently. And the idea that we should know about denormal numbers is that operations on denormal numbers are slow. Why are they slow? Because the Intel designers, when they were building the Intel CPU, they made a decision. Mostly when we see floating point numbers, they are not denormals. They are normal, right? This is the common case. So they built the processing of normal floating point numbers directly inside the floating point execution units. So they selected a fast path for the common case. However, sometimes you receive a denormal floating point number, so you have to react to it somehow. And the Intel designers implemented a slow path for this, which is using this microcode sequencer, which basically is some kind of small software layer on top of this microarchitecture that can generate and pump new instructions inside this whole machinery. So when they see a denormal floating point number, they will switch to this microcode sequencer, and it will pump out instructions for this microarchitecture to deal with this number. And after it's done, it will continue executing the other instructions behind it. Why is this important? Well, this was kind of a toy example, but when you have some kind of input, and suddenly when a different value of that input makes your processing time 5 times slower, this can lead to something like a denial of service attack. Like if your users are inputting floating point numbers inside your server, and they start to put in numbers that you didn't expect, and suddenly your server is processing them 5 times slower, this is probably another situation that you want to have. And again, if you want to make sure that this is indeed what is happening, perf comes to rescue. It has this performance counter called fp assist any. So this assist means that is switched to this microcode sequencer, how many times the CPU switched to some handling of a slow path for a denormal floating point number. How many times wasn't the floating point number fast? So we can measure it. Perf stat e fp assist any. Right, so with 0, there are no assists. With 1, there are no assists. For 0.1, there are almost 5 million assists. And this is a deterministic number because the number of iterations is deterministic. So this will be same in each iteration, which you, for example, cannot say about cache misses. They are usually different for each run, but this is deterministic. And when you use a different number, the number of assists will be different because based on the size of the number, it will take a different time to reach the normal numbers, and then it will take a different time to reach 0. So for example, when I have this 0.2, let's just time it. It's 0.33. When I start adding zeros, it actually gets faster because, yes, it gets to the normals faster, but since it's so slow, it will multiply the denormals, and very quickly it will get down to 0. Right? So it depends on the size of or the value of the number, how slow will the program be. And as I showed before, with 0.5, this doesn't happen because this is a power of 2, so it can be represented exactly, and it just goes down all the way to 0 without falling into this nasty denormals. So how can we fix this? Kind of like a nuclear option to fix this is just to use a compiler switch called ffastmath, which basically does a lot of things, not just deal with those denormals. It basically says to the compiler, sacrifice correctness to gain more performance. So it will break the IEEE rules about floating point. It will do a lot of stuff, and in that collection of things, it will also handle these denormals. If you want to have something more granular, you can set those, the following two CPU flags. The first one is called flush to 0, and it says that all floating point operations that output a denormal number will be treated as 0. So instead of outputting a denormal, they will just flush it to 0. That's exactly why is it called flush to 0. And the normals as 0 is the kind of like the opposite. All the normal inputs to floating point operations will be treated as 0. So instead of switching to the slow path, they will just say, this is 0, I won't care about those those bits because it's just such a small number. In code, it can look like this. You can either set some status register inside the CPU, or if you don't want to remember those hexadecimal codes, you can use those two macros. So let's try it. I cannot copy it from here. Oh, it doesn't matter. I will go all the way and so flash 0 mode, flash 0 on. So this sets the flash to 0 mode. I tested this just by itself, and this will make it approximately 2 times faster because the outputs will be at 0, but the inputs will be still slow. And the second mode is set the normals 0 mode, the normals 0 on. I hope that this is correct. It seems like so. Right, so compile. And now when I run example 2 with 0, 0.1, 0.2, 0.3, it's basically all the same, about 100 milliseconds. So the difference from before is gone. And if I want to just make sure, I can actually measure it. Right, so 0.3, but there were no floating point assists because the CPU was just like, whatever, this is 0. Okay. I have one backup example, but I'm not sure if I have the time. 8 minutes? Okay, so this will have to be super fast. But this one is also pretty known, so I think it should be fine. Again, without Google benchmark. This is kind of a longer code, so I won't explain all of it. But I receive from the input, again, some number. And this number will say how many threads I will launch. So I will spawn some number of threads. And those threads will repeatedly write to some double array. And they will write at an index which corresponds to their thread ID. So the first thread will write to position 0, the second thread will write to position 1, the third thread will write to position 2, and so on. This whole cycle machinery is just there to make sure that GCC actually generates a write to memory with O3, because apparently this is pretty difficult to do. So I actually want them to write to memory, not to just store to a register. So I have some additional code on top of it, but it's just that the first thread writes to element 0, the second thread writes to element 1, and so on. That's it. And they do this repeatedly. So again, compile example 3, I hope, yes. And if I run it with one thread, it will take, well, 2.71 seconds. If I run it with 2 threads, I would naively expect that it will take pretty much the same time. I have 4 cores on this machine, so if I just ran 2 threads that do some independent work without any synchronization, I would expect that the time won't change much. But actually, it seems that with 2 threads, it is slower than with 1 thread. Right? I don't have time now to kind of run multiple experiments. You will have to believe me. But the point is, it seems like there is actually some synchronization going on between them, but we cannot see it from the C++ code. So again, this is a pretty known effect. Any guesses? False sharing. Yay. Right. And I have to skip this. So now we're again talking about the cache system in the backend. And what happens when 2 cores are trying to access the same cache line. Right? So we already know that CPUs work with cache lines. They don't address individual bytes because that will be slow to transfer from memory. And we have an array that is contiguous, so let's say that at least the first 2 elements will hopefully reside in the same cache line. This is the memory with the array in it. Those are 2 cores, and each core has a private cache. So when core 1 wants to read the first element, it issues a read request, and the cache line is transferred from memory to the cache of core 1. Then core 2 wants to read B, and since they are in the same cache line, the memory system or the CPU notices this, and instead of transferring it from memory, it can just copy it directly from the cache of core 1, because that should be faster. Right, so this is actually pretty nice. We avoided a second load from memory, and both cores have their local copies. Everything is fast. However, a problem arises when they start to write. So when core 2 wants to write B, it changes B in its own cache line, but it also has to invalidate the copy of this cache line in all other cores, because it is no longer true that A and B have the original values. This core changed B, so all the other copies in other cores have to be invalidated. And this implies communication. Those 2 cores had to communicate together, therefore synchronize together somehow, to let them know that this should be invalidated. And what happens when core 1 wants to write A? Well, core 2 has to transfer its cache line, which is modified with the modified B, to core 1, so one form of communication. It has to invalidate its own cache line, because it is now changed by core 1. And all the other cores will also have to invalidate their potential copies of this cache line. Right? And this effect is called false sharing, because the cores are not actually accessing the same element in memory, right? Then we would have to synchronize manually. They are accessing different elements, or let's say different words, different integers. But since they are in the same cache line, they have to communicate together to make this work. And in this pathological case, it generates a lot of communication, and it makes the program slower. So this is the case in the program. We have some array of doubles. This is 8 bytes. This is a cache line, so 8 doubles. This is the kind of boundary between 2 cache lines. And we have 2 threads. And in my scenario, thread 0 was writing to this location, thread 1 was writing to this location, and this generated the conflicts. One way to fix this in this scenario would be, right, we have conflicts, would be to just say that each thread will work with its own cache line, and therefore we will avoid any conflicts, and our program should be faster. And I don't have to code to show this. We could see that if I change this, it would be actually faster, but I can at least show that there is another performance counter which says how many times did some core invalidate this cache line in other cores. And when I run it, let's say I run it with 2 threads. This number is 100 million. When I run it with 3 threads, or 3 cores, it keeps increasing. And if I run it with 4 cores, it's almost doubled. With 1 thread, this problem isn't there, just 16,000, because there are no other threads that would be invalidating the cache lines. Right? So again, some orders of magnitude difference in this performance counter. And you can fix this by making sure that if a lot of threads are accessing the same data or data that is needed to each other at once, you should align or pad your data structure so that they access individual cache lines. Right. Sorry for this. I have showed you some basic effects, but there are a lot of other effects, hardware things that you can demonstrate. NUMA effects, which will become very important in the upcoming years because our DRAMs grow, but they cannot, because they grow so much, we cannot make sure that accessing all parts of the DRAM will have the same latency. So non-uniform memory access is something that we should take into consideration when we care about performance, 4K aliasing, misaligned accesses, prefetching, non-temporal stores, bandwidth saturation, and a lot of effects. And you can find all those effects and some others at my repository, where I was kind of trying to gather a lot of those examples since last year. So if you are interested in this, you can visit my repo. You can create an issue where you tell me how I'm measuring random noise, how it doesn't make any sense. Or you can add your own examples. I would be really glad for that. So that is all. Thank you for your attention. Any questions? It's light, I know. Okay. Is there a mic or?
So when you said that fast math, there is a compiler function, compiler option that can improve the computation of your floating points. So is it not enabled by default in O3?
fast math is not enabled by default in GCC. However, I think Intel has it by default when you use optimization.
So in addition to O3, we have to mention this compiler flag.
I'm sorry?
In addition to -O3, this has to be provided.
Yes, in GCC, when you use O3, I don't think that fast math is included. I may be wrong, but I don't think so.
Right.
But the Intel compiler usually puts a lot of stuff by default so that it seems faster on slides. But if you enable the same things in GCC, you kind of can get to the same situation. So yeah.
Thank you.
Any other questions?
Hi, I'm referring to the force sharing issue. I believe that your processor should have SMT, right? So it's
I have turned turbo boost off. I have turned hyperthreading off.
Okay, so you turn hyperthreading off.
No, I have actually. Those were like 4 physical cores executing.
Okay.
No hyperthreads.
Okay. Have you tried with hyperthreading enabled?
Yes.
Because
so
if the two threads are
hyperthreads
on the same physical core, then you shouldn't have the force sharing. And then the question is, how does the scheduler schedule the 2 threads? Because that would be interesting.
I have tried it, but I didn't dig so deep inside. This is actually pretty hard to create a short example that would work with O3. Like if you look online, if you try all the examples, they work in debug mode, but when you turn on O3, there's no force sharing. So I just created this example painfully to make this effect visible. And yes, if you have 2 hyperthreads on a single physical core, they share the cache. So in this situation, it wouldn't happen. But I'm not sure that the Linux scheduler kind of can take. I mean, yeah, it knows about hyperthreads, but it probably doesn't look at individual cache lines. That I can't imagine that this would scale. But I don't know.
Yeah, of course. If you once you got to 3 threads, it's gonna have false sharing.
Yeah, of
anyway,
course.
So
If you have more than 1 physical core touching the same location, you have false sharing. Yes.
Okay. Thanks.
I think there was a question.
I was just interested in knowing, with the first part of the talk, there was something about the sorting and so on. Was actually the times also the sorting part of the times or not?
No. The sorting was not included.
Okay.
Yes, of course, if you sort your data, that is a slow operation. So this only makes sense if, for example, you sort once and then you do a lot of queries on your data.
Okay, thanks.
Usually sorting once and then doing a one search, it doesn't make sense. This was just like for the benchmark to show the effect. Okay, so that's it.